Okay, in module 2.4, we are going to work out examples of conditional probability. So we saw in module 2.3 definition of Bayes theorem and the general expression for Bayes theorem when we have multiple mutually exclusive events Ci leading to, in our context, failure F. So we are going to apply these concepts in module 2.4. Let's start with example 1. So we are given that a student distribution is shown in the table. And the student distribution consists of students of engineering, but they are in different disciplines of engineering: civil engineering, electrical engineering, mechanical engineering. They could be men or women. And the question that we are being asked is, what is the probability of a student being a woman and in mechanical engineering? Okay. And the second question is, what's the probability of a woman student studying mechanical engineering? This seems like a bit of a word twist. And the key message in all of these problems is converting verbal statements into probabilistic events and describing the probabilistic events mathematically. So the first question is woman and in mechanical engineering. So the emphasis on and is important here. And here, what's the probability of a woman student studying mechanical engineering? So in the second statement, we are given that the student is a woman, and we are asking the question, what's the probability that such a student would be studying mechanical engineering? So first thing we need to do is we have some raw numbers, and we need to turn them into fractions, and we need to define events. So what I'm going to do is to define events, C1 being the event that the student is in civil engineering, C2 being the event that any student is in electrical engineering, C3 being the event that any student is in mechanical engineering. S1 is the event that a student is a man. S2 is the event that the student is a woman. So now I have total number of students as 1000, so I divide each cell by 1000 to get the fractions. Okay, so the probability that a student would be in engineering and man or woman would be 1.0. And so now the first question is, what's the probability that a student is woman and in mechanical engineering? So in other words, what we are seeking is the probability that a student is woman and in mechanical engineering. So what we are seeking is the probability S2 and C3 or C3 and S2, and that probability is going to be 0.05. The second question that we are asked is, given that a student is a woman, what's the probability that she would be in mechanical engineering? So given that a student is a woman, what we are seeking is the probability that she would be in mechanical engineering, and that's a conditional probability question. So the first question is probability of C3 and S2, student is woman and in mechanical engineering. That's a straightforward one. Second one is a conditional probability, given that a student is woman, what's the probability that the student would be studying mechanical engineering? C3 given S2. And by Bayes theorem, we know that probability of C3 and S2 or C3 times S2, product rule, divided by probability of S2, which is 0.05 divided by 0.2, and that's 0.25. So that's the probability that given a woman, the student is in mechanical engineering. So it's always tricky to convert these verbal statements into equivalent events. So the process that we would need to follow in any of these probability problems is, first we have to convert verbal statements into events. So here, for instance, the simplest events are defined as C1. C1 is the event that a student will be a student of civil engineering. C2 is the event that a student will be a student of electrical engineering. C3 is the event that a student will be a student of mechanical engineering. S1 is the event that a student is a man, and S2 is the event that a student is a woman. So those are simple event statements. Then we ask the question, what is the probabilistic description of the verbal statement? What is the probability of a student would be woman and in mechanical engineering? So woman and in mechanical engineering, we interpret that as probability of event C3 and S2. And in the second question, we were asked to estimate the probability of a student being in mechanical engineering, given that the student was a woman. So that is then the equivalent mathematical statement of that verbal description is C3 given S2. And so then we can go through the process of using Bayes theorem and estimating the probabilities. So in example 2, we are going to illustrate how in practice we will apply conditional probability theorem, the Bayes theorem. So oftentimes, as I described before, in any product failure, we will have multiple causes. And in a laboratory environment, we will identify the probability of failure given a specific cause. And then we would go seek in field use environment, given that a failure has occurred, what caused the failure, which of the many possible causes contributed to the failure or led to the failure. So here is an example of that. So we have a GPS receiver, and there are many events that could potentially, many mechanisms that could potentially contribute to the failure of that GPS receiver not receiving a signal, with the probabilities that are shown here. A1 is solar radiation. The probability of that occurring is 0.0001. A2 is cloud cover, and the probability of that occurring is 0.005. A3 is receiver electronics failure. The probability of that occurring is 0.002. And you might have ground obstacles that also prevent you from receiving a GPS signal. You might be going through a depressed area which has a lower topography that prevents you from receiving signals. The probability of that is 0.04. And in a laboratory environment, what we would do is look at each of these situations in isolation, each of these mechanisms in isolation, and estimate the probability of failure under each of these mechanisms. So we will ask the question, what's the probability of failure under solar radiation? If I were to subject my system to solar radiation, what's the probability of failure, not receiving a signal? And that probability we estimate to be 0.3 here. If you had to have cloud cover, what's the probability of not receiving signal? And that we estimate that probability to be 0.01. And these numbers are all made up numbers. So, and you can next ask, if I had receiver electronics failure, what's the probability of not receiving a signal, etc., 0.005. These numbers are, like I said, made up numbers. And similarly, ground obstacles, what's the probability of failure of the system? You can say it's 0.0002. So now, in the event of failure, find the probability for the cause to be each of the above events. So in other words, if a system were to fail in field, then we would now want to know what caused the failure. That is, we want to ask the question, given F, what's the probability of A1 or A2, A3, or A4 given F? So what we do in lab environment is the reverse. So we would isolate, we would give an A1, we would focus on one failure mechanism at a time, test to figure out the probability of failure under that particular failure mechanism. But in use environment, it will usually be the other way. All right, so I'm going to switch over to my notebook so I can hand solve this problem. So what we are given is probability of A1 is 0.001, 3 zeros 1. Probability of A2, and these are all the probabilities of these events occurring, like cloud. The probability of solar radiation occurring is 0.0001. Probability of cloud cover occurring is 0.0005. That's how these probabilities have to be interpreted. And the third event, the probability of event A3 occurring is 0.002, and that's the receiver electronics failure. And probability of event A4 is 0.04. And we're also given probability of failure given event A1. And this is what we would do in a lab experiment. We would isolate a specific failure cause and ask the question, what's the probability that it will lead to system failure? And probability of failure given event A3 is 0.005, and probability of failure given A4 is 0.0002, and these will be typically obtained from lab experiments. And what we seek is probability of AI, the failure cause AI, given that failure has occurred. And in order to obtain this, so we would need to use the general statement of Bayes' theorem, so which states that probability of AI given F is probability of F and AI divided by probability of F, okay, because AI are mutually exclusive events. So in this case, we will assume that AI are all mutually exclusive. So this is by Bayes' theorem is probability of F given AI times probability of AI divided by summation probability of F AI. So there are many mutually exclusive causes that together lead to the failure event. And this again, you can write further as probability of F given AI times probability of AI divided by summation over I. Again, applying Bayes' theorem statement, so we can write this as probability of F given AI times probability of AI. Okay, so now we know from the lab experiments probability of F given AI. So therefore, we can go ahead and substitute and estimate probability of A1 given F, and that turns out to be 3 over 9.8. Probability of A2 given F turns out to be 5 over 9.8. Probability of A3 given F is 1 over 9.8. And probability of A4 given F is 0.8 divided by 9.8. Those are the 4 events, and so now we can go ahead and calculate the probability of a particular failure cause given the failure event. Go on to the next example. So in this example, we are told that a manufacturing company employs testers to check its parts for flaws, and not all testers are of equal experience. Okay, and the experience levels are classified into 3 groups. So group A is recent hires. They have under 2 years of experience, and 22% of the testers are recent hires, and 11% of them make a mistake when testing parts on any given day. So 22% of the employees are recent hires, are group A, they belong to group A, and 11% of them make mistake on any given day. And this data comes from historical records, right? And experienced testers are group B. They have 2 to 4 years of experience, and these testers form 43% of the employees, and only 3% of them are likely to make a mistake on any given day. And then there is a third group, which is super testers, group C, and they are the most experienced with 4 or more years of experience, and only 2% of them make a mistake on any given day. So we have 3 groups, and they all have different levels of experience. We know their populations: 11% for group A, 43% for group B, and the remaining for group C. And we know that 22% for group A, 43% for group B, and rest group C. And we know that group A makes 11% of them make mistakes. In group B, only 3% make mistakes, and in group C, only 2% make mistakes. So the first question is, on any given day, what percentage of testers make a mistake? Now, what is the total of the total employees? What fraction make a mistake when testing a part? That's the first question. Second question is, supposing a tester has missed a flawed part, what are the probabilities that the tester belongs to group A, B, or C? So in other words, this is similar to the previous example. Given a failure event, what's the probability that that occurred because of the person doing the tester belongs to group A, group B, or group C? Okay. And further question is a little involved. So what it says is that the recent hires were also put through some testing class, to improve their skills. And of those who went through the class, only 5% of them make a mistake in any day, opposed to 13% of the other hires. So if I further divide the 11% of mistakes made by group A, those who did training class, only 5% of them make mistakes, but whereas the ones who didn't do the training, 13% of them make the mistakes. So supposing you have an employee with 1 year experience, belongs to group A, and misses a flawed part, what's the probability that he or she had not taken the advanced testing method class? Okay, this is a fairly involved problem. In problems of this nature, it's critical to define events, and if possible, also to graphically depict the problem using Venn diagrams, as I will show here. So we are going to define events. Event A is employee belongs to group A. B is employee belongs to group B. And C is employee belongs to group C. Then we're going to define an event M, and we're going to say M is employee makes a mistake in testing. That's the event M. And it can occur because employee belongs to group A makes a mistake, or employee belonging to group B makes a mistake, or employee belonging to group C makes a mistake. And then finally we will also define other events to describe the situation where employee belonging to group A has taken a course or not taken a course. So let's start with part A. The part A, on any given day, what fraction of employees make mistakes? So really what we are seeking is probability of M. M is the event that employee will make a mistake. So therefore, what we are seeking is probability of M, and it can happen only one of 3 mutually exclusive ways. So employee belongs to group A and makes a mistake, employee belongs to group A and makes a mistake, or employee belongs to group B and makes a mistake. Okay, maybe I should write this as B and A M, B, M, or the employee belongs to group C and makes a mistake, which from Bayes theorem I can write as probability of M given A times probability of A. Okay, mistake given group A, the mistake rate, and similarly M given B times probability of B plus probability of M given C, probability of C. And I know these values, so I can go ahead and estimate these. So I know probability of M given A. We are told that 11% of group A makes mistake. Therefore, probability of M given A is 0.11. And we know the probability of an employee belonging to group A is 0.22 because 22% of the total number of employees belong to group A. And the probability of M given B is 0.03 because only 3% of employees belonging to group B make mistakes. So given group B, the probability of mistake is 0.03. And we know that 43% of employees belong to group B. And the third situation, we know only 2% of group C employees make mistake, and the population of group C is 35%, which is 1 minus 0.43 minus 0.22, and this, when you calculate, turns out to be 0.044 or 4.4%. So on any given day, 4.4% of employees make a mistake. Then let's go on to part B. So given a mistake or a flawed part, missed part, and what's the probability that the employee belong to A, B, or C? So given a mistake, what's the probability that the employee belong to groups A, B, or C? So what we seek here is probability of A given M, B given M, and C given M. Let's do one at a time. Probability of A given M is probability of M given A using statement of Bayes theorem divided by probability of M, which we've already calculated. And so this is M given A is 0.11 times 0.22 divided by 0.044, and this value is approximately 0.55. And similarly, probability of B given M is probability of M given B times probability of B divided by probability of M. That's probability of M given B is 0.03, and the population is 43%, 0.43, and divided by 0.044, and this number is approximately 0.29. And probability of C given M similarly is probability of M given C into probability of C divided by probability of M. That's equal to 0.02 times 0.35 divided by 0.044, and that's approximately 0.16. So if we find a flawed part, there's 55% probability that it came from member of group A. It was made by a member of group A. There's 29% probability that it was made by a member of group B, and 16% probability that it was made by a member of group C. The mistake was made by a member of group C. So now let's go on to the third part. And so we are given that a quarter of recent hires have taken a testing class. Okay, so this is a quarter of employees belonging to group A have taken testing class. Only 5% of these make mistake. So we are given this as well. And 13% of those who without class, who didn't take the class or without training, make a mistake. So the question that we are asked is, given a mistake by a member of group A, what is the probability that that person has not taken that the employee has not taken the training class? So that's the question. So what we are going to do is to define a new event. So define event T as employee has taken training class. Employee belonging to group A has taken a training class, say the training class. So what we seek, T complement would imply no training class. So given a mistake, what we want to know, given a mistake by a member of group A, what we want to know is what's the probability that this person has not taken the training class. So what we seek is probability that this person has not taken the training class, given that this person belongs to someone who makes mistake and group A, so MA. So this we know is probability from Bayes theorem. We can write this as probability of MA given T complement times probability of T complement, okay, divided by probability of MA, those that make mistakes and who belong to group A. And of the people who belong to group A, there are two ways they could make a mistake. Those that had the training, they could still make mistakes, and those that haven't had the training could also make mistakes. So we could write this further as probability of the denominator. We can write it as probability of MA given no training, members of group A given no training, times probability of no training plus probability of members of group A making mistake given training times probability of training. So we could write, so again, there are two possibilities there. They're bijointly, they give the probability of making a mistake of any member of group A. So now I can go ahead and substitute the numbers. So the probability of MA given no training is 13%. We've given that. And we know the probability of no training is 75%. So that's 0.75. We are told that only 1/4 of the employees belonging to group A have taken the training class. Therefore, 3/4 of employees belonging to group A have not taken the training class, and that leads to probability of T complement being 0.75. And we are also told that 13% of those who didn't take the training make mistakes. So that's where the first number comes from. And the denominator would be similarly 0.13 times 0.75 plus, and we know only 5% of those who take the training class make mistakes. So this is going to be 0.05 times, and we know that the population that takes the training class in group A is 25%. So that's 0.25. So you go through this number, and this turns out to be approximately 0.89. So the probability of recent hires who have not had training, given that an employee belongs to the recent hire group, group A, and who made a mistake, that person has not had a training class is 89%. Okay, so these are all applications of Bayes theorem in a reliability type context. With that, I'm going to conclude this particular module of examples of conditional probability.